We're going to start on problem 2 on our practice exam. So this is a question dealing with viruses are simple, beautiful, but deadly. Viruses are very simple but extremely deadly and well-designed pathogens. As seen below, the base plate will attach onto a cell. So the base plate's right here. Attach onto a cell and inject the DNA encapsulated inside the capsid head and replicate your virus. So that's how kind of these viruses work. So you have kind of this thin capsid sheath, DNA inside. It kind of attaches to your cell, shoots in the DNA, and then replicates, and then the virus, reproduces over and over and over and over again. So you can typically approximate the capsid head as cylindrical with a thickness of approximately 1 nanometer and an average diameter of 50 nanometers. The DNA is tightly packed, exerting an internal pressure of approximately 40 pascals. The capsid will burst when the engineering strain reaches a value of 3%. The Young's modulus of the capsid is 1 gigapascal. When I place this virus in a bath of deionized water, the water will rush into the capsid due to the osmotic pressure and exert some additional pressure on the interior of the capsid walls. So it says to write out the full stress and strain tensors for this stress state quantitatively at the instance of fracture. What is the additional pressure required to fracture the capsid? For what type of strain will the capsid fracture? And draw the fracture surface of the capsid. Be sure to explain your coordinate system. So when you were reading this problem, that's a lot to take in. The first thing that should have popped out into your head, you read the terms right here. I'll actually draw on mine. So you read the terms. Whenever you hear thickness, whenever you hear cylindrical, and whenever you hear diameter, you should pop in your head thin-walled pressure vessels. So the other thing is the initial delta P inside your capsid is 40 pascals. The Young's modulus for material, it's given. Again, this is a polymeric material, so you could be asked to kind of approximate it. And it said we're going to fracture when we reach a strain value of 3%. So we need to figure out what is this stress and strain tensor quantitatively, and what is the additional pressure required to fracture. So let's go ahead and start to solve this in Mathematica. So the first thing I want to kind of check is what is our condition for thin-walled pressure vessels? Well, we need to define our R. So let's define thickness first. So 1 times 10 to the minus 9, that is a nanometer. The radius is going to be 50 times 10 to the minus 9, and I'm going to divide that by 2. I can do that in my head. That's 25. So that will be my radius. Let's make sure. I'm going to just suppress that output because we really don't need to know that. I'm interested a little bit in why is it 0.5. That's much better. So I want to make sure that my ratio of R divided by T is greater than 10. It is indeed, so we can use our thin-walled pressure vessel approximation. So so before we even get started with my, now we're working with stress strain tensors. If you look kind of further down in this problem, we're going to have to write out the principal stress tensor, and then we're going to need to do some rotation as well. Full 3 principles. Actually, we don't need to do rotation necessarily here, but we will do some rotation. So what I'm going to do, again, it's just a nice kind of, now that you have Mathematica at your disposal during an exam, I would already have basically your matrix loaded up. So I'm going to do my T matrix, so my rotation matrix. So I'm going to have that as C squared, S squared, 2 times SC. I'm going to cheat and use this in later examples. S squared, C squared, minus 2 times S times C. I'm going to have to multiply this right here. And you should remember this from the problem set, S times C, or just have it defined already in your notebook. And then C squared minus S squared. Let's just take a look at that. T matrix, matrix form. That looks nice. So I'm also going to find C equals cosine of theta. And then I'm going to type in degree. So we're in degree mode here. S is going to equal sine of theta in degree mode. Ooh, what's going on here? There we go. Now let's reevaluate our T matrix. And we could see what's happening right here. I'm going to zoom out just a little bit. Yep, so I could look at that nasty T matrix. Again, we'll use that a little bit later. So we have a thin walled pressure vessel. So I know my stress tensor automatically, and we'll actually draw our coordinate system. Actually, let's draw our coordinate system first. So I am going to work in this coordinate system where we have, we're going to have 2 here, we're going to have 1 here. I'm going to have my thin walled pressure vessel. This is obviously going to be our, in this one direction here, our sigma 1 is going to be equivalent to our sigma hoop, and then our sigma 2 is going to be equal to our sigma L, where we know, and we'll define what hoop and longitudinal stresses are in just a second. Now, I already know, and actually the problem might ask for a little bit later, but I know that the hoop stress is larger. Hoop stress is equal to 2 sigma L. So I know that the fracture surface should go right here. So it should fracture like this because, again, you're pulling, it will materials will tend to fracture in the regions of highest stress. Now, you could observe a fracture pattern like this, the opposite, where it's like in the longitudinal direction. That means that there's something wrong with your material. There's some defect. There's something that's happening where the stress now is concentrated basically in that other direction. So that's why the material fractured here. But ideally, it should fracture just like this. A kind of picture of your fracture surface for thin wall pressure vessels. So let's go ahead and define that stress tensor. So it's going to be sigma H, and then the rest of them are 0. We have plane stress conditions here. So then it's sigma L, or excuse me, 0, sigma L, and then the rest are 0. And then these are all just 0. I also have the same condition that my strain is going to be equal to epsilon, I'm just going to call it EH, the hoop strain, and then it's going to be the hoop EL, the hoop stress, and that's the rest. That's it. So that is our strain tensor, that is our stress tensor. So now let's kind of calculate these quantities. So what do we know about this problem? Actually, let's define sigma H. We know is going to be equal to H. Let's define some of that problem. Is equal to del P times R divided by T. And then we're going to know that sig L is equal to sig H divided by 2. We also know that our EH is equal to 1 divided by Y, our Young's modulus, which in this problem, let's define that actually up here as well. Y is equal to a gigapascal, so 1 times 10 to the 9th. Y and E are kind of, you'll see them both in literature for the Young's modulus. I'm not using E because it's already built in function in Mathematica, the exponential. So I'm going to use Y here. I also know I'm going to need nu. So my Poisson's ratio for biomaterials is 0.4. You are not going to necessarily be given that. Again, that's kind of written in the notes, so you want to make sure to have that available. So EH is going to be 1 over I times sig H minus nu times EL. And you could define EL as well. EL is the same thing, except we switch sig L minus nu times sig H. That's it. So I'm going to just close these outputs and define. So you can now see in our expression here, we're also kind of, again, we're trying to just define and get quantitative values for all of these, everything in here. So all that we have left to solve is this del P. Once we have del P, we're going to be able to kind of write the rest of our kind of values and plug and chug in here. Because once we have sig H and sig L, we're good to go. So the question now becomes, the capsule will burst when the engineering strain reaches a value of 3%. What strain, again, assuming that we have a perfectly fine thin wall pressure vessel, what strain is going to lead to fracture? Which strain is larger, EH or EL? It's the hoop strain, right? Because the hoop stress is larger. So we are going to solve for, we know that EH is equal to 0.03, because again, 3%, I don't want to work in percent, I want to work in strain values. And I want to solve simultaneously, actually I'll solve EL later. So I want to solve for, when EH is 0.3, let's solve for del P. So my del P is 1.5 times 10 to the 6 pascals. So we will now, you can also now plug in, so if I set del P equals 1.5 times 10 to the 6 pascals. So that's the del P required to fracture. So the additional del P, so because the question asks you, initially we are at a 40 gigapascals, so we need to do del P minus 40. That's going to be the additional pressure required to fracture material. So again, very, 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 it's basically insignificant. This is kind of your value here, but that's the technical answer to this question. So we've solved this. We now know our stress, EH is going to be equal to 0.03 because we want the stress and strain tensor right at fracture. So EH is this, EL, it's already given here. So now I can write my stress. Actually, let me now reevaluate here. So my stress, actually, let me evaluate this one more time. So my stress, my matrix form, is going to be this value right here, 3.57. Again, twice this. My strain, my matrix form, is going to be this. So 0.03, that value right there. And that's it. We're good to go. So that's all kind of we're dealing with here. So I hope so we've already answered essentially the first part of this question, which is write out the full stress and strain tensors for this stress state quantitatively. What's the additional pressure required to fracture? That was our additional. For what type of strain will the capsid fracture? We already answered that. And draw the fracture surface of the capsid. Be sure to explain your coordinate system. Right here we did that, and 1 and 2. So write out the principal stress tensor and the rotation required to get to this state. So let's look at my stress tensor. Am I in the principal stress state? Yes, because you're in, that's the beauty of the thin wall pressure vessel. You're already in principal stress state because all the shear values, all your shear stresses are 0. So the rotation required to get to your principal stress state is 0. Do the same for maximum shear. So what is the rotation required to get to maximum shear? So we're already in the principal stress state. We know to get your maximum shear, you're going to rotate theta of 45 degrees. And you could do that clockwise or counterclockwise. So here's where I could do T matrix, which I kind of did previously, multiplied by stress. And I'm going to replace theta with, it could be 45 or minus 45. I'm going to use my clockwise or counterclockwise rotation. So I'm going to have that positive 45 degrees. And that is my full stress tensor there. And actually, let me do matrix form. That's it. That gives us, again, when we do this rotation of 45 degrees, this is going to give us our stress tensor. Again, what this problem is asking for, right? The principal stress tensor, we already have that, and the rotation is 0. For maximum shear, it's 45 degrees, and we've written this out here. And now it's asking us to draw the Mohr circle for the full 3D principal stress tensor. What is the maximum shear stress for the 3D state? So all we have to do is, I'm going to kind of draw it on here. Let me see if I can get some room. Yes. So let's look at our initial stress state here, when we're in the principal stress state. So my sigma 1, I can't do both at once. So my sigma 1, excuse me, told you graphically. So sigma 1, my largest principal normal stresses is going to be sigma h. My sigma 2 is going to be sigma L, and my sigma 3 is going to be 0. So if I want the full 3D Mohr circle, tau, sigma, this is going to be sigma h, this is going to be sigma L, and this is going to be my, you can kind of reread this, sigma 1, sigma 2, and sigma 3. So you're going to have a circle here, you're going to have a circle here, and you'll have a circle like this. So that's your 3D Mohr circle. And now it asks you, in the 3D Mohr circle, what's the maximum shear stress for the 3D state? Well, that's just going to be the radius here, right? So it is going to be the radius of this kind of, the radius here, this radius is just going to be equal to, sigma h over 2. That's it. That's your value of maximum shear right here. We have answered, let's see what we've, always lots of questions in my questions, sub-questions and sub-questions. Fantastic. So now it says we want to model the mechanical behavior of this virus with a polymeric material on the orange curve here, right here. Assess whether this is a good candidate to model the material under this stress state by seeing if the material will yield via Rankine or von Mises criteria. So we need to figure out, we're trying to model this behavior, and we're trying to see, is this a good candidate to model material under the stress state by seeing the material yield via Rankine, Tresca, von Mises criteria. So all we're doing here, what is the yield stress? So when we're dealing with Rankine and Tresca and von Mises criteria, let's kind of write those and remind ourselves of what those criteria actually are again. So we know that Rankine is just going to be, so our Rankine criteria, we're just going to look at, is sigma 1 greater than sigma y? So we need to figure out what is the sigma y in this chart. So we're linear, 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 and then, so I'd say about, let's say our sigma y is about approximately 300 megapascals. Yeah, excuse me, 300 MPa. So that's sigma y. So that's Rankine. Tresca is going to be our sigma 1 minus sigma 3 is greater than or equal to sigma y. And then I am not even going to, actually I'll try von Mises. Von Mises, in terms of principal stresses, which you already have, is that sigma effective, which is going to be the square root of 1/2 times our sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus all this under that plus sigma 3 minus sigma 1 squared. It has to be greater than or equal to sigma y. So let's test and see if any of these criteria will, if the material will yield according to these criteria. So, or this new polymeric material. So I know that my sigma 1 is equal to sigma h. I know that my sig 2 is equal to sig L, and my sig 3 is equal to 0. So sigma 1 is 3.75 times, so really this is basically sigma 1, sigma 1 is equal to, let's go back here, 37 gigapascals, or 37 megapascals, 37.5. So will it fail via the Rankine criteria? No, it's not going to fail. So this stress is not going to, it's not going to yield. So it should not yield if we're modeling it with this material. So because the yield stress here, 300 megapascals is greater than 37.5. Same thing for Tresca, right? Same value because sigma 3 is 0. And now let's kind of plug and chug for this guy right here. So square root of 0.5 times sig 1 minus sig 2 squared plus sig 2 minus sig 3 squared plus sig 1 minus sig 3 squared. Here, close it, there, and again, still much lower than that yield stress. So the question is, assess whether this is a good candidate to model the material under the stress state. It's a horrible model, right? Because again, this material didn't not only yielded, it fractured at these stresses. So that's kind of the hidden answer to this problem. But again, it's more kind of practicing, essentially using these yield criteria to see whether the material will yield or not. So yeah, I hope you like that question. Next one, it's going to be bend but don't break just yet. And we're going to do some yielding, looking at more stress strain curves, and then our favorite deformation mechanism maps. So we'll get to that in a bit. All right, see you in the next video. Thanks, bye.